Okay, everyone, Assalamu alaikum. Let's begin. Let's start with uh, our today's class. So today we want to do, in fact, today and also tomorrow, we want to do just practice questions on this concept of friction. Okay, so I'm not sure if I've told you this before, but these are the two big topics that we have in M1. The first one, forces in equilibrium, and then the next one that we will be doing is kinematics. And after this, the rest of the three topics, they're not going to take a lot of time. But we do need to spend quite some time on these first two topics because these are the biggest topics. And on these topics, in most papers, you get two questions each. So you get two questions on forces and equilibrium generally, and two questions on kinematics. So you do need to spend some time practicing questions on these topics in detail. All right. So what did we do in the last session? We basically understood this concept of friction, which is really important because now the next worksheet, the questions that I've assigned from that, they depend on the concepts that we did in the last session. So what's friction? Friction is a type of contact force that opposes the motion of an object. We've done one contact force before already, which was normal reaction. Friction is another force. Uh, friction opposes Friction is the force applied by a surface on an object, and that basically opposes the motion of an object. Okay. Now, it always acts parallel to the surface. Remember normal reaction that always used to act perpendicular to the surface. Friction, on the other hand, acts parallel to the surface. Okay. We did some examples here. We said that friction always has a maximum value, which depends on two things, mu and r. Okay, what's mu? Mu is the coefficient of friction. That's basically a number that tells you about the roughness of the object, and R is normal reaction. We'll discuss this in detail why it's a reaction that the maximum friction depends on. But now you need to remember this: F max, the maximum value of friction is given by mu times R. Then we said there are three different cases that we can have in such problems. Generally, the object can either be uh, in equilibrium, which is non-limiting. Then it could be limiting equilibrium, where it's the extreme point of equilibrium, where the object is just about to move. If you were to just increase the force even slightly more. And then the last one was when you have the object in motion. Okay. Now, for each of these cases, you need to know the relationship between friction and the maximum value of friction. Okay. You need to know this relationship. When you have limiting equilibrium, F equals mu r. Friction is at its maximum value. That means it's equal to mu r. When you have the object in motion, in that case as well, friction equals mu r. And then if it's just equilibrium, sometimes they tell you that the object is in equilibrium and ask you to prove an inequality. In those cases, you need to use this idea that friction is less than or equal to mu r because equilibrium means it's either non-limiting or limiting. So it's either less than mu r or equal to mu r. So if you write both of those conditions combined, that becomes F less than or equal to mu r. So this is what you need to remember from this. F is equal to mu r when you have limiting equilibrium or the object in motion, and F is less than or equal to mu r when it's equilibrium and you're not specified whether that equilibrium is limiting or non-limiting. And then there were some phrases that we discussed about the description of limiting equilibrium. Sometimes they explicitly tell you that the equilibrium is limiting. At other times, they will be using phrases like these, that the object is just about to slip, slide, or move, or the object is on the point of slipping, on the point of sliding, on the point of moving. These also indicate that the object is in limiting equilibrium. And whenever you have a limiting equilibrium, that should remind you of this, that F equals mu r. F is not always equal to mu r. It's only equal to mu r when it's limiting equilibrium or when the object is in motion. Only in these two cases does this condition apply. Okay. So yeah, that's what we did in the last session. Then we did one question from the worksheet. That was question number 1 from the worksheet. And I asked you to do a number of other questions from the worksheet as well. Now, first of all, I want to hear from you. How many of you are done with at least 5 questions from the worksheet? Practicing is extremely important. Please make sure that you're doing that alongside. Otherwise, uh, you're not going to remember much. You will need to do everything from scratch again, and you don't want to do that. There's not much time left now to be able to do that. The level of detail in which we're doing things right now, you will not have time to do that again before your exams. So make sure that you're making use of this opportunity well and not lagging behind. Okay, that's good. That's most of you who have done at least 5 questions. Now you can let me know which questions you have problems in. We can start from some of those today, and then we will be spending tomorrow on this as well, and maybe another day as well, because there are some extra questions as well which I'm going to post, which you will also need to do apart from the worksheet. There's some questions from recent papers that I want you to have a look at. Uh, so it will take time. So maybe 2 more days after today, or at least one is definite. That's tomorrow, inshallah. So let me know. Let me know which questions you have problems in, so we can start from some of those today. Yes. So those of you who attempted questions, you did not have any problems until now? Is that what you're saying? Okay. All right. So what I'll do then is I will uh, choose some of these questions then, and we can have a look at those questions specifically. Let me find a few from the worksheet then. Okay, so let's start with a relatively simpler one for today. Okay, so let's start with this one that Rajal is asking about then. Let's start with this. So question number 20, let's start from that. Okay, please make sure that you are not hesitating to ask questions. I want to make this more interactive. That's how you learn math. You try some problems, you end up getting stuck at something, then you ask about that. And when it gets clarified, you're much more likely to retain that for longer. When you ask a specific question and that gets clarified, then you will remember that for longer. But if I just do questions and you're just looking at them, you will understand them during class, but you're not likely to retain that for much long for long basically, and that's going to be a problem because then you'll have to redo a lot of the stuff, and that's not going to be helpful. Okay, so let's start from this one. So this is the question that Rajal is asking about, question number 20. Let's have a look at this. Question number 20 from the worksheet. Okay, so I'll give you 30 seconds to read this question. I'm just going to connect my charger in the meantime. So take 30 seconds, read the question statement, and then we're going to start. Then we're going to start doing it. Okay, so I hope you have read the question now. Let's have a look at this. So it says a particle P of weight 5 Newton it's attached to one end of each of two light and extensible strings of length 30 centimeters to 40 centimeters. So we have a particle of weight 5 Newton here. So the weight acting downwards is 5 Newton. We have the length given. You can see all of that information on the diagram. The other is attached to this, a rough rod. So the rod that we have on top, that's a rough rod. That means there's going to be friction. When you have a rough surface, you have friction. There's a small ring S of weight W Newton. So this ring S has weight W. So at S, we have this downward force of W Newton acting. The system is in equilibrium. Now, when there's equilibrium, that means the opposite forces are equal. The forces acting towards the left side and the forces acting towards the right side, they're equal. The upward forces and the downward forces, they're also going to be equal. Okay, now in the first part, it says, by resolving forces acting on P in the direction of PS or otherwise find the tension in the longer string. Okay. Let's first represent the forces that we have. What are the forces acting here? We have 5 Newton, the weight of this object P. Then we have tensions, right? This particle P is attached to two strings. There's one string towards the left side and there's another towards the right side here. There's going to be one tension acting in this direction. Let's call this T1. There's going to be another tension acting in this direction. Let's call this T2. These are the two tensions that we have, okay? They're going to be different. Why? Because these are two different strings. When you have two different strings, the tensions are different. So we are writing them as T1 and T2. Okay, they're going to be different tensions. At point P, these are all the forces that are acting. There's no other force. Okay, so there are three forces. And these three forces are in equilibrium. What we need to do is we need to find the tension in the longer string. What's the longer string? The longer string is this 40 centimeter one. So we want to find the value of T2. That is what we're looking for, the value of T2. Now, how do you find this? You first of all need the angles, right? We don't have any angles given here. So we can't resolve T2 or T1 or any of these forces. These lengths that they've given, the whole point of giving these lengths is that you can find angles using these lengths. Now, what are the lengths? The lengths are 30, 40, and 50. It's a right angle triangle like this. What you can do is you can say, let's call this angle θ1. Okay, how can you find the value of θ1? You can use tan, sine, or cos, whichever of these ratios you want to use. So what if I have to use, for example, cos of θ1? Cos means the adjacent side is 30. That's 30. Over the hypotenuse, that's 50. 30 over 50. I can find the value of θ1 from here. Okay. So that's one idea. Let's find the value of θ1. What do you get? Anyone tell me what this value is? θ1, cos inverse of 3 over 5. What do we get? We can do the same thing here with θ2 as well. Let's call this. In fact, once we have θ1, we can find θ2 directly then. Can you tell me what θ1 is? 53.1. Okay, can we be more accurate? Because this is working, you want to be more accurate in your working. Otherwise, your final answers might be off by 1 decimal place, and that can end up making you lose marks.
So 53.13.
Okay, 0.13. All right, so 53.13. That's what we have here. Now, if this angle is 53.13, then what about the remaining angle? We can just subtract this from 90. That's going to give us 36.87. Okay, it's a right angle triangle. The remaining angle is going to be 90 minus 53.13. So we have these angles now. We want to find the tension in the longer string. That's T2. Now, one idea is that we resolve the forces, right? We can resolve the forces. How would we resolve the forces? One idea, I'm not asking you to do this right now. Just bear with me for a moment. One idea could be that you resolve T1. There are going to be two components, one acting in this direction and one acting in the vertical direction. If this angle is 53.13, this angle is also going to be 53.13, alternate angles. This would be T1 cos of 53.13, and the other one will be T1 sine of 53.13. And then if you were to resolve T2, that would be in this direction. If this angle is 36.87, then this one is also 36.87. Again, alternate angles. So we have T2 cos of 36.87, and the vertical component would be T2 sine 36.87. And then what we can do is we can just equate the opposite forces. We can equate left forces acting towards the left side to the forces acting towards the right side. T1 cos 53.13 equal to T2 cos 36.87. That's one equation. And the other equation could be T1 sine 53.13 plus T2 sine 36.87 equal to 5 Newton. These could be two equations that we could make here and then solve them simultaneously to find the value of T2. That is one idea. Okay. All right. This is one idea. You can do that, and that will give you the correct result. However, if you look at the question, what does the question say? It says by resolving the forces acting on P in the direction of PS. In the direction of PS. Now, it's slightly confusing, but it makes things quicker. I'm going to tell you about this, and then we will discuss another method as well, which I would recommend that you do instead if you don't understand this, but I'll explain this, what they mean by this. By resolving the forces, so this is one method, right? So what I've done here is, this is one method. You make two equations. One equation, T1 cos 53.13 equals to T2 cos 36.87. That's one equation. The other equation would be T1 sine 53.13 plus T2 sine 36.87. That equals 5. Okay. You make these two equations, solve them simultaneously, find the value of T2, and you will get the result. Okay. But now let's try to understand what they are telling us here. Okay, let's just get rid of this. All right. So these are the original forces. Now, what are they telling us? They're saying by resolving the forces acting on P in the direction of PS. Now, what we did there was this option or otherwise. So they're not making it compulsory to use what they have suggested. They're saying you could use some other method as well. That's okay. However, they're suggesting something. By resolving the forces acting in this direction, PS. Now, if they give you a hint like this, generally, that hint is going to make things easier for you. So let's try to understand what they mean in the direction of PS. Now, remember when you have an inclined surface, and on an inclined surface, if we have forces like this, if we have a particle here, it has weight acting in the downward direction, a reaction acting in this direction, maybe some other force acting in some other direction. In an inclined surface, we used to resolve forces parallel to the surface and perpendicular to the surface. We did not used to resolve them horizontally and vertically in that direction, in that case. So one possibility was that we resolve the forces horizontally and vertically. And inclined surfaces, we said, we would be resolving forces parallel to the surface and perpendicular to the surface. In both cases, you see the components that we have, they are perpendicular to each other. So basically, it's not necessary that one component has to be horizontal and the other has to be vertical. The components that we are finding, they can actually be in any direction. In 99% of the cases, we use this convention that, okay, if we don't have a surface, just use horizontal and vertical components. And if we have an inclined surface, have components parallel to the surface and perpendicular to the surface. This is the logic that works. This is the convention that works in 99% of the problems that we have. However, mathematically speaking, any directions would work. So even if you did not have a surface, you could resolve forces like this if you wanted. One force in this direction and another in this direction. As long as the two directions that you take, they are perpendicular to each other. That's all that we want. That resolve them in directions that are perpendicular to each other. So resolving could work in any two directions, but generally we use these directions. Now what they have done in this question is, they have asked us to resolve the forces in the direction of PS. What's the direction PS? Direction PS is this. So they are suggesting that you might find it helpful to resolve forces in the direction of PS. That means one component in the direction of PS and the other would be perpendicular to that. That's in this direction. Why is that going to make things easier for you? Because you would only have to resolve this 5 Newton force then, because T2 is already in direction of one of these directions. And T2 is in the direction of PS, and T1 is perpendicular to that. So you don't really have to resolve T1 and T2 anymore. You only have to resolve 5 Newton. That's the only force you have to resolve. And you will see that makes things much easier in this case when we resolve this 5 Newton now. How do we resolve this 5 Newton force? Let's figure out the angles. This angle is 53.13. If that angle is 53.13, what we can say is, so if we have two components of 5 Newton, one is going to act in this direction and the other is going to act in this direction. We need one of these two angles, either this angle or this angle. How do you find those two, any of those angles? What we can say is, if this angle is 36.87, this is also going to be 36.87, right? Corresponding angles, this angle and this angle, these are corresponding angles. And if that's 36.87, what about this one? This is 53.13. And then what we can do is we can find the components of 5 Newton in these two directions. The component that's adjacent to the angle. This one is going to be 5 cos of 53.13. And the other one is going to be 5 sine 53.13. And now you just equate the opposite forces. What are the opposite forces? T2 equals 5 cos 53.13 and T1 equals 5 sine 53.13. And you notice you don't really have to solve any simultaneous equations. Now you get the two results directly from that. That's why they've given us this hint that this could give us directly that T1 equals 5 sine of 53.13. We don't even need that, but we could find that like this as well. What we need is T2, the tension in the longer string. What is T2 equal to? We could get that in one single step. That's 5 cos of 53.13, and that will give you the result directly. Okay, what do you get from this? 5 cos 53.13? 3 Newton?
Yes, sir.
So that's the tension in the longer string. You could get this directly like this by resolving forces in the directions that they have suggested. Does this make sense?
Yes, sir.
Any problems, anyone? Rijal, make
Sir?
sense to you? Yes, Abdullah.
Sir, how did you make these components 5 cos 53 and 5 sin 53?
Remember the directions? The green highlighted directions. These are the directions that we have to resolve the components and that we have to find components in. 5 Newton is acting vertically downwards. So 5 is going to have these two components. One here. This is one component and the other is going to be here. We figured out this angle 53.13. the component that is adjacent to the angle that has cos, and the component that's on the other side of the angle that has sine. We've learned this before, right? The component that's adjacent to the angle, that's going to have cos. The component on the other side of the angle that has sine. That's all that we have to do. Do you have any specific question here? As in, where are you getting confused? You understand how we find the angle 53.13?
Yes, sir.
Then it's straightforward after that. The component that's adjacent to the angle, that's cos, and the component on the other side, that's sine. Okay. All right. So this is one idea that we use the directions that they've specified. Now, some people find this confusing, that why are we resolving them in this direction? In that case, you could either use the method that we discussed before, but remember, there was another method that we also did. When we have equilibrium and three forces only, remember Lami's theorem? You could just use this, and that will make things just as quick as this has made. That might be even simpler to use for some of you. So that could be another idea. Let me show that to you as well, and then we move on to the next part. So the last idea here could be, so I'm telling these methods so that you know that you could do it all these different ways, and then you can decide which one works better for you. Okay, so because different people prefer different methods, so then you can decide which one works better for you. Okay, so we have these forces acting, right? At the particle P, at the point P, we have a 5 Newton force acting downwards. We have T2 acting towards the right at an angle, T1 acting towards the left at an angle. There are three forces, and those three forces are in equilibrium. Now, whenever you have this, you can use Lami's theorem, and that makes things a lot quicker and easier as well. All we need is the angles between these forces. We already know this angle is 90. Can you find the other angles? If this angle is 53.13, this is also 53.13. Then this is 90. And similarly, this angle is going to be 36.87. And this is 90 below this. Now I can just represent that diagram separately here to make you understand that better. So we have one force acting downwards, that's 5 Newton. There's one force acting towards the right at an angle, that's T2. And there's another force acting in this direction, like this. This angle is 90. What about this angle? 53.13 plus 90. The angles between these two forces, T1 and 5 Newton, that's 53.13 plus 90, that's 143.13. And then the remaining angle, 36.87 plus 90, that is 126.87. Three forces, those three forces are in equilibrium. Let me just write that here. Why can we use this? Because we have three forces. This condition is satisfied. We have equilibrium. This condition is also satisfied. You can use Lami's theorem. You can say T1 over sine of 126.87. That should equal 5 over sine of 90, and that should equal T2 over sine of 143.13. Okay, so these are the forces and their corresponding angles. This is what the Lami's theorem is going to give us. Now, what we can do is, since we're looking for T2 only, we can use this part of this equation. We can say T2 equals 5 into sine of 143.13 divided by sine of 90. And that should also give you the same result, that is 3 Newton. Okay, that could be another idea that you could use here. Lami's theorem, that's also very quick. Once you figure out the angles, that's all that you have to do after that. Is that all right? Any problem
Yes,
with
sir.
this?
Yes, sir.
Okay, so you might find this easier than resolving forces in this direction, and that's perfectly okay. They have given us this option. Otherwise, that means you could use another method as well. You don't necessarily have to do what they're suggesting. So you could use Lamy's theorem here as well. Okay, good. Let's look at part 2 now. Part 2 says, find the magnitude of the frictional force acting on S. What's S? S is this ring that we have on that rod. We want to find the magnitude of the friction force. Now we have to look at the forces acting at the point S. Okay, now what I'm going to do is I'm just going to get rid of these lengths here. We don't really need them, right? The whole point of giving those lengths is to help you find the angles, right? Now, once we have the angles, there's no use of these lengths. I'm going to just get rid of them. What we want to do is we want to represent all the forces acting at the point S first of all. Okay, remember all the forces that you have to think about yourself. Weight, normal reaction, tension, friction. Make sure that you're representing all the forces that are applicable from those four forces. Weight, we have already represented, that's W. Tension, if you think from the perspective of the ring S, tension acts away from S and towards the string. What's going to be that direction? It's going to be acting in this direction now. Okay, this is the direction in which tension acts for the point S. And what's that magnitude? We have found that in the first part. They've made us find this in the first part. 3 Newton. So there's tension in this direction that has a magnitude of 3 Newton. Okay, so that's one force. Then what about normal reaction? Do we have normal reaction in this case? Do we have normal reaction?
Yes, sir.
Why?
Sir, because the ring is in contact with the rod.
With the rod, and rod is a surface. Whenever we have a surface involved that is in contact with the object, we have normal reaction. Now, normal reaction always acts perpendicular to the surface, right? Now, you are pulling the ring downwards. It's being pulled downwards because of the weight and also because of this tension. Reaction is going to act opposite to that. That means in the upwards direction. The direction of reaction is this. This is reaction, normal reaction. Okay, so we have reaction. What else? Do we have friction? It's a rough rod, so we do have friction. Friction always acts parallel to the surface. That means it could either be on the right side or the left side. Which one of the two is it going to be? Left or right?
So
Right.
the right side.
Right, because the tension is trying to pull this ring towards the left side. There's a component of 3 acting towards the left side. Friction is going to oppose that. It's going to resist that motion, and that's going to act to the right side. This is the direction of friction. These are all the forces acting at the point S. Now, the only force acting at an angle is 3 Newton. Let's resolve that force. There's one component of 3 Newton acting in this direction. That will be 3 cos 36.87. It's the component that's adjacent to the angle. And the component on the other side of the angle, that is going to be 3 sine of 36.87. Now the question says, find the magnitude of the frictional force acting on S. Okay, so we have that here. We have F acting towards the right side, 3 cos 36.87 acting towards the left side. Since the ring is also in equilibrium, we can just equate these forces. We can say the force acting towards the left side, that should be equal to the force acting towards the right side. And that should give us the result. The force acting towards the left side on the ring should be equal to the force acting towards the right side. On the left side, we have 3 cos of 36.87. On the right side, we have friction. That gives us the value of friction. Okay, what's that?
2.4 Newton.
2.4, is that exact 2.4?
It's 3.99996.
Okay, so that means if you were to use an exact value of this angle, that will be 2.4 Newton. So that's the result. Okay, that's all that you had to do in the second part. Now the third part says, given that the coefficient of friction between S and the rod is 0.75 and that S is in limiting equilibrium. Now, if it's limiting equilibrium, what does that mean? F equals mu R. Okay, since it's limiting equilibrium, F equals mu R. We need to find the value of W. Now, all we have to do is just equate the opposite forces here as well. Upwards forces should equal the downward forces. That means R should equal W plus 3 sine 36.87. Okay, that's what we do. We say upwards forces should be equal to the downward forces. Upward forces R, and the downward forces are W and 3 sine 36.87. Okay, these are the downward forces and upward forces. Okay, we're just equating them. Now, what do? We have to find the value of W. That's what we are looking for. And we're given the coefficient of friction. The coefficient of friction is 0.75. Okay. So what we can do now is we can say, let's find, we already have this, F equals 2.4. Now, since F equals mu R, we can say 2.4 equals mu into R. What's the value of mu? Mu is 0.75. What we can do is we can find the value of R from this, right? We know friction value already. Using friction and the value of mu, we can find R. What does this turn out to be? 2.4 over 0.75? Is that 3.2? Divided by 3 into 4, right? 3.2?
Yes, sir.
Yes, sir.
3.2 Newton. You put that here, and that gives you 3.2 equal to W plus 3 sine 36.87, and that should give you the value for W. All right, what do we get?
1.4.
1.4. Again, is that exact?
1.399.
Okay, so 1.4 Newton, that's the value of W that we were looking for. So all we did in the second and third parts was that we just equated the opposite forces. We represented all the forces acting at the point S, and we used F equals mu R because in the last part we had limiting equilibrium, and that gave us the value of the friction, reaction, and also the value of W. Any problem with this? Any questions on this?
No, sir.
No? Okay, let's have a look at another one then. This was question number 20. Any other questions from the worksheet? Anyone? No? Okay, so let me find another one that's slightly complicated. Yeah, let's try question number 15. Question number 15 from the friction worksheet. How many of you are done with this? Can I raise a hands? Those of you are done with question number 15 already, this one? Is anyone done with this already? Question number 15? No one yet? Okay, let's try this. So again, take 30 seconds and read the question statement, then we'll try this. Question number 15. This is a good one. Okay, so we have a block of mass 20 kg that is at rest on a plane inclined at 10 degrees to the horizontal. A force acts on the block parallel to a line of greater slope of the plane. The coefficient of friction between the block and the plane is 0.32. Find the least magnitude of the force necessary to move the block. Now, in mechanics, I would recommend that whenever you don't have a diagram given in the question, always make your own diagram. That makes things easier to understand. In this case, we don't have a diagram given. It's going to make things easier if you just draw this diagram yourself. Okay, so this is what it might look like. It's an inclined surface, right? And Do we have an angle? Yeah, so the angle of the plane is 10 degrees. That means it's less steep than this actually. Let's make it like this. 10 degrees is the angle. There's a block of mass 20 kg at rest on the plane. So there's this block like this. This block has a weight of 20, no, it has a mass of 20 kg. So the weight of the block is going to be 200 Newton that acts vertically downwards. Now, a force acts on the block parallel to the plane. So whenever it says parallel to a line of greater slope of the plane, all that means is parallel to the plane in the direction of the plane. Okay. The coefficient of friction is 0.32. Find the least magnitude of the force necessary to move the block, given that the force acts up the plane. Which force? This force that they're talking about, this parallel force that you're applying, if this force acts up the plane, what's the least force necessary to move the block? What's the least force necessary to move the block? Okay, let's try to understand this. Let's represent all the forces acting on this block first of all. So we already have the weight represented, that's acting vertically downwards. What other forces do we have? We have normal reaction, it's a surface. So surface has a normal reaction, that's perpendicular to the surface. That's here. That's one force. And then there's this force F. They're saying that this force acts up the plane. Let's call this force something. We could call this F, P, whatever you want to call it. There's this force acting in this direction. Let's call this capital F. So I often represent, in fact, I always represent friction with small f. And then with capital F, we have another force, let's say. That's acting in this direction. That's trying to make the object move. Okay. Do we have any other forces acting here? Do we have any other forces acting here? We don't have tension because there's no string involved. Weight, we've already represented. Reaction, we have already represented. What about friction? Do we have friction?
Yes, sir.
Yes, sir.
Which direction does that apply in?
Downwards that
opposite.
side.
Down the slope, right? Down the slope,
Yes.
because we are trying to move the object towards the right side. Friction should oppose that. It should act to the left side. Okay, because we're trying to move the object in this direction. Now let's resolve the forces first. Reaction, friction, and this force that you're that you're applying on the block, they're all acting either parallel or perpendicular to the surface. Only weight is acting in a different direction. Let's resolve weight. So there are going to be two components of weight, one acting in this direction and the other acting perpendicular like this. Right? These are the two directions in which the weight is going to apply. Now, how do we resolve weight? Remember, if this angle is 10, we said this angle here is also going to be 10. Right? Why? Because this is 80 and then the remaining angle is 10. So the components that you get are 200 cos of 10. The angle, the component adjacent to the angle, that is going to have cos, and the component on the other side is going to have sine. So we have 200 sine of 10 here. We have resolved the forces as well. Now, parallel to the plane, we have F, this friction, and 200 sine 10. And perpendicular to the plane, we have reaction and 200 cos of 10. What's the least magnitude of the force necessary to move the block? Now, first of all, there's one thing that you need to remember throughout mechanics. When you have a block moving on a surface, that movement is always going to be along the surface. So it's going to move along the surface. It's going to slide along the surface. It will never be perpendicular. It can never be like this. It can't be a parabola, like in this direction or in this direction. That is not part of our syllabus. In our syllabus, we only have one-dimensional motion in a straight line. Okay, so it can't be like this, that the block moves in this direction, right? or in this direction. That's not part of our syllabus. 2D motion cannot happen. It's only 1D motion in a straight line. What that means is, since the block is sliding along the surface, the forces acting perpendicular to the surface, they are always going to be equal. Okay? Since there's no movement perpendicular to the plane, reaction in this case should equal 200 cos 10. Okay, these have to be equal. Okay, so we say these are equal. Upwards force. So according to the surface, remember what we said. How are we going to label left, right, up, down? If you're standing on the surface, the left side is this. The right side is this. This is upwards and this is downwards. Okay, these are the 4 directions that we have. Upwards and downward directions, the forces acting in these directions, they're always going to be equal. Okay, because the block cannot move perpendicular to the surface. Now, when that happens here, upward forces R, downward forces 200 cos 10. We can find the value of R from here. Since we have friction involved, we will need this R. So I'm just going to calculate that first. 200 cos 10, what do we get from this?
196.96.
196.96 Newton. Thank you. So that's the value of R that we have. Now let's think about the forces acting along the surface. The force acting toward the right side and the left side. Are they also going to be equal? They would be equal if the block was in equilibrium. Okay, if the block was in equilibrium, F would equal friction plus 200 sine 10. What we're looking for is the least magnitude of the force necessary to move the block. Now, if you want to move the block, in which direction is the block going to move? Towards the right side? If you want to move the block, the force acting towards the right side, that should be greater than the forces acting towards the left side. Only then the block is going to move, right? The block is going to move if this force is greater than friction and 200 sine 10 combined. Only then the block is going to move. Make sense? So the right side, the force acting towards the right side, should be greater than the force acting towards the left side for block to move towards the right, towards the right direction. Is that okay? That means F should be greater than friction plus 200 sine of 10. And that will give you the least force necessary to move the block. How would that give you this value? You have 200 sine 10. You can evaluate that on your calculator. What about friction? Friction is equal to mu times R. Why is friction equal to mu times R? Remember this? We said F is equal to mu R when the object is in limiting equilibrium or when the object is in motion. So if the object starts moving, friction would be equal to its maximum value, which is mu R. So in this case as well, when the object does start moving, we can say F is equal to mu R. F is equal to mu R because the object is in motion. Okay, so that means mu R plus 200 sine 10. And that gives us F greater than mu. What's mu? Mu is 0.32. That's given in the question. Into R, we have found that above. That's 196.96 plus 200 sine 10. What's that value? 200 sine 10?
34.729.
34.729. And then what do we get at the end? What's the final result?
97.7562.
97.7562. If we wanted to round that off, we would say this is F greater than 97.8 Newton. Now, what we are looking for is the least force required to move the block. What's the least force required to move the block then? We would say the least F required to move the block is 97.8 Newton. Now, you might be confused. It says greater than 97.8. Why are we saying 97.8? Well, F is a continuous variable, as in force can be any value in decimals, 97.8, right? This force F can be any value in decimals. So if it has to be greater than 97.8, what does that mean? What can this value be? It can be 97.800000000, and then infinitely many zeros, and then maybe a 1 at the end. Even slightly more than this is going to make the object move. When you round that off, it still turns out to be 97.8. Okay, so you can't write it as 97.9. That would not make sense, because greater than 97.8, you also have 97.81. You also have 97.801. What about 8001? Then what about 80000? Then infinity many zeros and then 1. Okay, so you just want the force F to be slightly greater. When you round that off, that is still 97.8. So you'll just write that same value here. The least force required is 97.8.
So,
Is that okay?
shouldn't we just write that least F is greater than 97.8?
That's obvious. That's understandable. It says greater than 97.8. You've already mentioned that above. They are looking for one particular value, the least magnitude of the force. They're looking for one particular value. Okay, so the least value
Okay,
that
sir.
we have is 97.8. Okay.
Yes, sir.
All right, let's look at the second part now. Second part says, given instead that the force acts down the plane. So this force that you're applying, now they're saying this force acts down the plane. Now what happens in that case? Everything is going to remain exactly the same as before, except the direction of the force F. And because of that, you will see that the friction direction will also change. Let's just represent all of that again. Now you will be doing this in an exam using a pencil. You will be drawing that figure using a pencil, so that once you're done with one part, you can just erase what you don't need anymore or what you need to change, and use that same diagram for the second part as well. Because M1 papers, the recent ones, you will see that they are quite lengthy. So you can't afford wasting a lot of time. I've said this before as well, I think. So just a reminder about that. Now, reaction is still in this direction, and this is still, weight is still in that direction. The components of weight are also going to be the same. The only thing that changes is the force F is now acting down the plane in this direction. And because of that, friction now acts in the opposite direction, because the friction will try to stop the object from moving down the plane. So that's going to act up the plane now. Now, nothing has changed in this direction. Perpendicular to the plane, everything is still the same as before, right? So upward forces are, downward forces 200 cos 10. So we still have this thing valid. This is still valid, that the upward force is equal to the downward force, and R equals 200 cos 10. That is still valid. Okay. Now, if you're applying a force F in the downward direction, what's the least magnitude of the force required to move the object now? Now, since it has to move towards the left side, now we say the force acting towards the left side should be greater. What does that give us? That gives us F plus 200 sine 10, and we say this force should be greater than friction. Again, the object is in motion, so we can say F plus 200 sine 10, that is greater than mu R, because since the object is in motion, we're talking about the object moving now, so friction is still at the maximum value. We say F plus 200 sine 10, that is greater than mu, which is 0.32, into R, which is 196.96, and that will give us the value for F here. F should be greater than what? What do we get?
28.297.
28.297. That can be rounded off to 28.3 Newton because this is the final answer. Now we say the least amount of force required in this case is 28.3 Newton. And that's what we were looking for in the second part. It's almost exactly the same. It's just that the forces directions have reversed and everything else is exactly the same. Make sense?
Yes, sir.
Now, this is one way of doing this using inequalities. You can also do it thinking of like this, as in the process will be exactly the same as this. But instead of thinking of this inequality, you could think of it from this perspective that the object will remain in equilibrium if the opposite forces were equal, right? So remember, there are three stages. You have equilibrium, simple equilibrium, and then you have the extreme point of equilibrium, which is called limiting equilibrium, and then the object starts to move. Okay. What we can also do is we can think of limiting equilibrium case, that is the cutoff point where the equilibrium position is going to end and the object is going to start moving. So limiting equilibrium is kind of the transition between equilibrium and motion. So limiting equilibrium basically gives us that cutoff point at which the block is no longer going to remain in equilibrium and it's going to start moving. So instead of using inequalities like this, we could think of it like this as well. Since we're looking for finding the least magnitude of the force necessary to move the block, we could think of it like this. We could say, let's consider this as a case of limiting equilibrium with the block just about to move to the right side. Right? Could think of it as a limiting equilibrium case with the block just about to move to the right side. And then you could treat this as an equation like this. You would get the same result at the end, 97.8, and you would say 97.8 Newton acting in this direction, that would make the object to be in limiting equilibrium. Okay, so that's the cutoff point at which if you were to even slightly increase the force a bit more, the object will start moving. Okay, so you could get away with using equality signs here as well, and thinking of it as a limiting equilibrium case, and that will also work because that gives you that cutoff point at which the object switches from equilibrium to motion. That could be another way of doing that working as well. Everything remains exactly the same. You just change your perspective and think of it as a limiting equilibrium case. That will make you write these inequalities as equations instead. The result is going to be the same. It's just about thinking of it slightly differently like that. Does that make sense?
Yes,
So
sir.
in the marking scheme, if you see, sometimes they do use something like this. They, instead of using inequalities, they might have used equations. Don't get confused by that. They would basically be considering the limiting equilibrium case and then saying, okay, this is the cutoff point. And now, even if you were to slightly increase the force a bit more, the object will start moving. And that happens a lot, actually. We will be talking about this later. Whenever you have friction involved and you're looking for the least value of a force or sometimes the greatest value of a force, you think of this limiting equilibrium case because that is kind of the cutoff point for the object to remain in equilibrium or to just start moving. Limiting equilibrium is that. extreme point. So when you're looking for least value or greatest value of something, you're kind of looking for extreme values of course. And those extreme values are normally found using the case of limiting equilibrium. So you'll find this a lot in questions. Whenever they ask for least or greatest values, you will be using the case of limiting equilibrium there. Okay, but we will kind of write it down later formally as well, so you can remember that. But that's for later. That's it for today. I will leave you with this. You can try some more questions for the next class. Tomorrow we want to do a few more questions from the worksheet. There are some that I specifically want you to have a look at. In fact, not just have a look at, try. There is question number 40 from the worksheet. And there is question number 50 from the worksheet. They're very similar, but important questions 40 and 50. And then you can also have a look at '66 perhaps. Yeah, this is also a good one. It also asks you for least value of something, right? So it's kind of similar to what we've just done. It'll require you to use that limiting equilibrium case. So 40, 50, 66. And then you have 34, which requires you to prove an inequality. 34. And there's there's another one very similar to this, which is 73. So these 5 questions I'll be targeting tomorrow, that we do these 5 questions at least. In fact, yeah, so this is all that we would actually be able to do in tomorrow's class, unless you have some other questions. We can also discuss those. But I have these 5 questions in mind that I want to do. So I would want you to try them first. So 40, 50, 73, 34, and 66. At least these 5 questions, please try them. And then the questions that you have problems, and we will be discussing them tomorrow, inshallah. All right. Okay, so that's it for today. I'll see you again tomorrow. Allah Hafiz.